Alright, so in the last section we learned about some chord properties. We learned about some tangent properties in 6.1, and this is all building on our lesson, our entire section here on circles. So today let's talk a little bit about some arcs and some angles. To start us off, let's review. If I have a circle, I got 2 points on that circle. I'm going to name this circle G because that's the center point. I've got 2 points, H and I, on the circle. If I create that segment from the center to a point on the circle, it's a radius. That's another radius. And what I've also done is created a central angle. Central angle HGI, and it intercepts arc HI. And we know that those two degree measures are the same. Well, now let's learn a new kind of angle. Remember, a central angle has the circle's center as its vertex. But now let's put a vertex on the circle itself. When I have an angle with a vertex on the circle, I call it an inscribed angle. So I've got angle HJI here, and angle HJI is an inscribed angle. So on the screen I have a central angle, I have an arc defined, and I have an inscribed angle. But look at how I've built this inscribed angle. It intercepts the same arc that my central angle, angle HGI, does. Let's review what we know about central angles and arcs. If I look at the measure of this central angle, and I compare it to the measure of this arc, the degree measure, they will be the same. Those degree measures are the same because the degree measure of an arc is equal to the measure of the central angle that intercepts it. But what does that tell me about the degree measure, the angle measure here of angle HJI, this inscribed angle? Well, remember here the inscribed angle HJI has this, it intercepts the same arc as central angle HGI. But if I get this circle really small, a little bit smaller here, it becomes pretty evident that even though it intercepts the same arc, it's not the same size. So I can't use that reason. Let's use a little bit of inductive logic. And before we use this inductive logic, I'm kind of setting this up so we could see it visually. But there are a lot of great proofs, and we can go over some in class. But Euclid actually came up with a good proof of how we can determine the measure of an inscribed angle compared to its central angle and the arc that it intercepts. But for our purposes here, let's just make an approximation, an inductive guess. If I have this is a radius, the center G is one radius away from the center of arc HI. If I made sure that they were in line and that J fell on the same diameter, it wouldn't be one radius, it would be 2 radii away. It would be twice as far from the center of this arc as the center G is. So J would be twice as far away from the arc as G is. So if it's twice as far away, how do you think that affects its angle measure? Well, if I know that G's angle measure is equal to the arc it intercepts, and J is twice as far away, it should follow that angle HGI is what? How about half as much? Now again, that is simply an inductive with a visual. We're looking at it lined up nice and neat here. And there is a more thorough proof from Euclid that shows that no matter where I move the vertex for this inscribed angle, its measure will be half the measure of the arc that it intercepts. So if I leave my arc alone, it's still equaling 80 degrees. If I slide the vertex for the inscribed angle that intercepts that arc across the circle anywhere, it will always be half the measure of that arc. So the first property we can learn about our inscribed angles is that they are always equal in measure to half of the arc measure that they intercept. The arc measure here is 80 degrees. The inscribed angle that intercepts it is 1/2 of that, or 40 degrees. So let me go ahead and hide my radii right now. Move my inscribed angle up here. I'm going to make another inscribed angle, but I'm going to make it intercept the exact same arc. So if I have two inscribed angles and they're intercepting the same arc, not sure how I did that guy. I named the line. Let me hide that really quick. Hide that label. Show that label. Sorry about that. If I have, let's go back again. This inscribed angle is equal to 1/2 the measure of the arc that it intercepts. The arc it intercepts, arc HI, is 80 degrees, so the measure of angle HJI is 40 degrees, 1/2 that. Well, this angle, inscribed angle HLI, also intercepts arc HI. So its measure is 1/2 of the arc measure, which is 40 degrees as well. And I can conclude that anytime two or more inscribed angles, any inscribed angles that intercept the same arc are going to be congruent. Let's double check really quick. If I measure angle HLI, it is 40 degrees. So any any inscribed angle that intercepts the same arc will be congruent to another angle intercepting the same arc. And again, it doesn't matter where I move these inscribed angles to. If I bring them together, we see they are in fact the same. And if I move them around the circle, the measures don't change at all. Now, if I start over with this, take all these things away, I'm going to put another circle out here. And I'm going to create, see if you guys can figure out what I'm doing. I'm going to create a chord, find the midpoint of it, create a perpendicular line through it, which we know is going to pass through the center. Make this thing set up a little bit nicer here. I'm going to find where that perpendicular bisector to the chord intersects the circle. And then I'm going to make a line segment between it. If I hide all of those guys, now I've got circle M, and I have a diameter that I've made through it. Let's go hide that point. I have a diameter that I've made through circle M. So now I have this diameter. Doesn't matter how I change my circle. That's always a diameter. Now what's going to happen if I put a point out here, point in, and I make an inscribed angle from that point that leads to the endpoints of a diameter? Well, remember, when I create a diameter, I also create two arcs. Well, they're two special arcs. I've got arc P in Q, which is a semicircle, and I have arc QOP, which is also a semicircle. Now the inscribed angle P in Q intercepts semicircle QOP. So what should the measure of angle P in Q be? Well, if we recall, the arc measure of a semicircle is 180 degrees. So the angle measure should be 1/2 of 180 degrees, or 90 degrees. So I could say that any angle inscribed in a semicircle, no matter where it's inscribed in and at, will be equal in measure to 90 degrees. Any angle inscribed in a semicircle is a right angle. Alright, so now we got a couple of facts about inscribed angles. Inscribed angles are equal to 1/2 the measure of the arc they intercept. If two inscribed angles intercept the same arc, then they must be congruent, and any inscribed angle inscribed in a semicircle is a right angle. So now let's get rid of all these guys again. Let's set up another special case here. Watch what I can do with Sketchpad. I'm learning this thing out. I'm learning how to use this guy, and I'm constantly amazed by it. What if I put 1 point, 2 points, 3 points, 4 points? I have just inscribed, what is this figure? All I can call it is a quadrilateral. I've just inscribed a quadrilateral. Hide that little point there. I've inscribed a quadrilateral into circle S. So I've inscribed quadrilateral TUVW. And all of these angles at the vertices of the quadrilateral are inscribed angles. So what can I say? Can I make a statement about the angles that are opposite from each other? The non-consecutive angles. Angle W and angle U. Well, if we take a minute to look at it, we realize that angle W intercepts arc TUV. And angle U intercepts arc VWT. Or, in this case, we could just call it VT. What do I know about the measure of arc TUV? The measure of this arc plus the measure of this arc down here. Well, look what we just made. If we add those two arcs together, we get a complete circle. So they must be 360 degrees. So what does that mean about the measure of this angle plus this angle? It must be 1/2 of 360, or 180. And that makes the opposite angles of an inscribed quadrilateral supplementary. Not only that, but we call this inscribed quadrilateral a special name. We call a quadrilateral inscribed in a circle a cyclic quadrilateral. So the same supplementary property applies to angle T and angle V. because they are opposite angles in a cyclic quadrilateral, they are supplementary. Anytime I have an inscribed quadrilateral, inscribed in a circle, the opposite angles will be supplementary. All right, we're almost there. We're almost through with this lesson. 6.3 is a long one. We got one more property to talk about with these angles and arcs. In this one, we're getting away from our inscribed angles and we're moving just to the arcs, all right? Now, I'm going to make a line. Get over here to my line tool. I'm going to make a line. And then I'm going to choose this line. And I'll choose this point. I'm going to construct a parallel line. So now, it doesn't matter how I move these lines, they will stay parallel to one another all the time. Now there's a special relationship, let's see if you can see it, between the arcs and these parallel lines. Now if I move way out here, it's pretty obvious that arc is not congruent to this arc. And if I move it down a little bit, that arc changes measure, but this arc stays the same. So there's no measure relationship between the arcs outside of parallel lines. But what if I look at the arcs on the inside of parallel lines? We'll just call this one point A. And this can just be circle B. All right, so we've got arc XY and arc AZ. They're both captured between two parallel lines. Let's see what happens if I measure those two arcs. Wow. Hey, wait a minute. Those two arcs are congruent. And will it matter where I move this parallel line to? It won't. Because the lines are parallel, the distance between them will be the same all along their length. If I move this point further away, all points get further away as well. If I move this point closer, all points get closer as well. And they get closer at the same rate. So the distance from A to this parallel line is the same as the distance from X to this parallel line. And this arc measure, XY, will always be the same as this arc measure, AZ. So the arcs captured between two parallel lines passing through a circle will always be congruent. And that, ladies and gentlemen, finishes up 6.3 and readies you for the quiz. So you've got a couple of videos to review. You've got some conjectures to put into your notes from 6.1, 6.2, and 6.3. And you have some homework assignments on your assignment sheet that you can complete and to prepare you for the upcoming quiz on 6.1 through 6.3. Feel free to go back and watch these videos. You can send me an email and ask me questions on them. And of course, you can ask questions in class when we go over everything.